Hello, welcome back to Math 152. Today we're going to start talking about probability, chapter 4, section 1. So what we're going to talk about is constructing sample spaces, computing and interpreting probabilities, and then approximate probabilities using the empirical methods. So let's talk about constructing a sample space. So a probability experiment, here's the background for doing a sample space. A probability experiment, that's all about what this is talking about. We're going to be doing probabilities, calculating if we can determine how likely something is going to happen based on the randomness of things, okay? So a probability experiment is one in which we do not know what any individual outcome will be, but we do know how a long series of repetitions will come out. For example, if we toss a fair coin, we do not know what the outcome of a single toss will be, but we do know what the outcome of a long series of tosses will be, about half of them heads and half of them tails. So the probability of an event is the proportion of times that the event occurs in the long run. So for a fair coin, that is one that is equally likely to come up heads as tails. The probability of heads is 1/2 and the probability of tails is 1/2. So the law of large numbers, the law of large numbers says that as a probability experiment is repeated again and again, the proportion of times that a given event occurs will approach its probability. So this is the classical probability or the theoretical probability that we have calculated based on just the likelihood, the equally likely times that an event will occur. Based on, so that's the calculation, and what the law of large numbers says is that if we start keeping up, and we track an experiment and keep doing this experiment over and over and over again, the average of all of those times will approach its probability. So if we keep just averaging out what we see. So the collection of all the possible outcomes of a probability experiment is called a sample space. It is just what we expect of if we do an experiment, what is the possible outcomes that we would get. If we toss a coin, we're only going to get a heads or a tail. If we roll a die, we're going to get 1, 2, 3, 4, 5, or 6. Those are the only possible ones that we're going to get on a 6-sided die. And if we get a 0 or a 7, we know something's wrong. So describe the sample space for each of the following. If I toss a coin, the sample space is just going to be what possibilities of the outcomes are what? Heads and tails. So here's our set notation, and in proper form the sample space is SS equals heads or tails. So what about the sample space for a roll of a die? Well, we're only going to get 1, 2, 3, 4, 5, or 6 out of that simple die. So that's our sample space. Selecting a student at random from a list of 10,000 at a large university. So if we go select one at random, our whole sample space is those 10,000 students, right? So it could be any one of those 10,000. So the sample space consists of the 10,000 students' names or the students themselves. We are often concerned with occurrences that consist of several outcomes. For example, when rolling a die, we might be interested in the probability of rolling an odd number. So rolling an odd number corresponds to the collection of outcomes 1, 3, and 5, and that's from our sample space of 1, 2, 3, 4, 5, and 6. So in general, a collection of outcomes of a sample space is called an event. So it's just the outcome. Did we get a 1? So if I wanted the event being just a 1, it would be a 1. And in this case, it was the 1 or the 3 or the 5. So once we have a sample space, we need to specify a probability of each event. This is done with a probability model. That's basically all of these set items that we have, the event that we have set up, our sample space, and that's kind of our model. We're not physically doing the experiment, but we're just doing analysis with our model. So we use the letter P to denote probabilities. For example, we denote the probability that a tossed coin lands heads by the probability of heads in this simple one. In general, if A denotes an event, the probability of event A is denoted by P of A. So here we're going to compute and interpret probabilities. So another way of looking at probabilities is just a proportion of times, or the percentage of times that we would think that that outcome could happen. So percentages are just basically from 0 to 100%. Probabilities correspondingly go from 0 to 1. So if an A cannot occur, then the probability of A is equal to 0. So when we were rolling that die, I could ask you what's the probability of rolling a 0 when I do that die, but it's not going to happen. So it's probability. There's no way that it can come from the sample space. So there's 0 ways that I can select it out of the 6 possibilities. So the probability would be 0. And if I had the heads, if I tossed a coin and I said, what's the probability of the event occurring of a heads or a tails? Well, that's 1. It's either going to be a heads or a tails. There could be nothing else. So that's certain to occur. So when we calculate, we're going to calculate if a sample space has n equally likely outcomes and an event A has k outcomes, simply counting the possibilities. You remember that 1, 3, and 5, we would just count 3 over the 6. In this case, we're just going to say whatever the outcomes in A that matches the event, and then number of outcomes in the sample space. So that's the basic calculation of a probability. In the Georgia Cash Floor Lottery, a winning number between 0000 and 9999 is chosen at random. With all the possible numbers being equally likely, what is the probability that all 4 digits are the same? So if we go through, we've got what? 10,000 possibilities, right? So out of the 10,000 possibilities, I'm just looking for the ones for my event that they're all the same. So it could be 0000, 1111, they match, 2222, all the way up to 9999. That's 10 out of the 10,000 possibilities. 9999 plus the 0. So now the probability of all 4 digits being the same, there's only 10 ways that matches that all 4 digits can be the same, but there's 10,000 possibilities. So the probability is 0.001. So sampling an individual from a population is also a probability experiment. The population is the sample space, and members of the population are equally likely outcomes. So sampling is a probability experiment. There are 10,000 families in a certain town categorized as follows. 4,753 own a house, 1,478 own a condo, 912 rent a house, 2,857 rent an apartment. These are out of 10,000. And a pollster samples a single family from this population. What is the probability that the sampled family owns a house? So, owns a house. There are 4,753 families that own houses out of the 10,000. So the probability would be simply that counting analysis. 4,753 divided by the 10,000. Okay. So our probability between 0 and 1 is 0.4753. The number of families who rent is 912 plus 210. So this is what is the probability that a sampled family rents. Now in this case, the first one just owns a house, right? But this one just says basically rents. Well, I have 920 that rent a house and then 2,857 that rent an apartment. So the number of families who rent, is add these up, are 3,769. Therefore, the probability that a family, if I picked at random, would be 3,769 divided by the 10,000, and that would be 0.3769. So in many cases going forward, we're gonna talk about an event being unusual. An unusual event is one that is not likely to happen. In other words, an event whose probability is small. There are no hard and fast rules as to just how small a probability needs to be before an event is considered unusual, but one that we will use as a rule of thumb is this. Any event whose probability is less than 0.05 is considered to be unusual. I could define it some other ways and use that, but that 0.05 is going to be something that should be thought of when they're asking about unusual. So in a college of 5,000 students, 150 are math majors. A student is selected at random and turns out to be a math major. Is this unusual? Well, let's see. We've got 150 math majors. We could randomly select out of that 5,000 an individual, and the probability would be the 150 out of the 5,000. So this 150 out of 5,000, if I do the division, I come up with 0.03. Less than 0.05 is what I need to compare it to as far as being a usual or unusual event, and that would be an unusual event being less than 0.05. So we can approximate these probabilities using the empirical method. Okay. So the law of large numbers says that if we repeat a probability experiment a large number of times, then the proportion of times that a particular outcome occurs is likely to be close to the true probability of the outcome. The true probability being that we calculated through theoretical or a classical probability. We did counting experiments. How many ways can this event happen out of the total number of outcomes in the sample space. So the empirical method consists of repeating an experiment a large number of times and then using the proportion of times an outcome occurs to approximate the probability of the outcome. So in this we don't know what the true probability is, and what we need to do is just run this, use the empirical method, do the experiment enough times that it seems to be evening out. It approaches some number that keeps getting, really close to this, and that's the empirical probability. So in a recent year, there were 2,046,935 boys, 1,952,451 girls born in the U.S. Approximate the probability that a newborn baby is a boy. So if I did the number of boys, the 2,046,935 over the total, this plus that would be the proportion, and we would use that to approximate if we knew what the classical or theoretical, we could calculate it, it would approach that, and this will give us an approximation of what it would be just by we did this enough times that it's pretty large. So here is the total number of births. If we add these up, here's the number of boys out of the total number, so 0.5118. So we can approximate the probability of being born a boy is 0.5118 using empirical probabilities. And if we did, I'd like to make that, so if we did this twice, if we redid this with, we had almost 4 million, if we looked at 6 million, this number would probably change a little bit, and we would get another approximation. The more we do it, we'd get a little better probably reading of what it should be. So here's what we've covered so far. We talked about the law of large numbers. If we knew what the classical probability is, we can enumerate everything, count them, do the calculation. If we do the experiment, it would approach that number if we did it large enough. And then if we can kind of go down here to the bottom, we can approximate the probability using that empirical method. We just keep doing it enough times that it starts looking like it's getting closer and closer to some number. It's not changing much. If we double it, triple the number of experiments, this number would be getting closer and closer. That's that approximation. So know your definitions of probability, sample space, and event. how to compute probabilities with equally likely outcomes, and then what we talk about for unusual, if the probability of that event occurring was less than 0.05. So I hope you enjoyed this lecture. We'll see you next time.